Hello friends. So today we are going to discuss the questions from the year 2019, and these are the total 20 questions, and all these 20 questions are from the mains. So first question, and it is asked that an object is at a distance of 20 meter from a convex lens of focal length 0.3 meter. The lens forms an image of the object. If the object moves away from the lens at a speed of 5 meter per second, the speed and direction of the image will be. So here we are given three things. First is a distance object, that is our u is given to us, and that u is given to us at 20 meter. And then we are given a focal length, that is our f is given to us as 0.3 meters. And we are also given the speed of the object. So we can say du by dt is also given to us as a 5 meter per second. And we are supposed to find out the speed of the image. So first of all, let's try to find out what will be the, you can say, the equation of the image, and based on this we can easily differentiate it and get the speed of the image. So we start with the basic formula, which tells us that 1 upon f is equal to 1 upon v minus 1 upon u. And from here we can write this as, let me call this as equation 1, and we can just modify it and find the relationship of v upon u, and that will be coming as f and u plus f. So let us call this equation number 2. Now if we differentiate equation 1, okay, because we need to find out the velocity, and we differentiate equation 1. Focal length will be, you can say, constant, because lens is fixed. Its focal length will be constant, equal to, so its derivative will be equal to 0. So we get this as 0 is equal to minus 1 upon v square dv by dt plus 1 upon u square and du by dt. And we just can modify it. We are going to get this as 1 upon v square dv by dt is equal to 1 upon u square and du by dt. And this can be further written as, we are only interested in dv by dt, so we can write dv by dt is equal to v by u whole square, and this is du by dt. And we already know the relationship or ratio of v upon u in equation 2. So we can say, using equation 2, we get dv by dt will be equal to f upon u plus f whole square will be equal to du by dt. And we are already given all these values, and here the velocity, the object is equal to minus of 20. So we substitute it, we get dv by dt will be equal to, focal length is our 0.3, and we have our u, that is minus of 20 plus 0.3 whole square, and du by dt is given as 5. And if we solve that, we can get that dv by dt will be approximately equal to 1.16 into 10 raised to the power minus 3 meter per second. And 1.16 is only 1, and it will be towards the lens. So option number D is the correct one. Or we can say from here, towards the lens. Towards the lens, and option D is correct. Option D is correct. Next question. Here it is asked that a plano-convex lens of refractive index mu1 and focal length f1 is kept in contact with another plano-concave lens of refractive index mu2 and focal length f2. If the radius of curvature of their spherical faces are each and f1 equal twice f2, then mu1 and mu2 are related as. So we have two lenses, plano-concave and plano-convex lens, and we have to find out the relationship between mu1 and mu2, that the respective refractive indexes. Okay. And we are given that the relationship between f1 and f2 is given to us. So we are going to consider the both lenses one by one. So first is a plano-convex. So we have a plano-convex lens, and we can just draw an approximate figure for that. It will be something like this, and its focal length is given as f1, refractive index mu1. So we can write that 1 upon f1 is equal to mu1 minus 1, and the standard formula is 1 upon r1 minus 1 upon r2, and its r1 will be equal to infinity. So this becomes 1 upon infinity minus, and this comes minus of r. And the standard formula is 1 upon f is equal to mu minus 1 and 1 upon r1 minus 1 upon r2. And from here we get that our f1 is equal to, this comes as r upon mu1 minus 1. Now we can consider our plano-concave lens. And plano-concave will be something like this. Once again, same formula. So we get 1 upon f2 is equal to mu2 minus 1, and we have this once again 1 upon infinity, and this will be 1 upon r, rather plus r. So this gives us that our f2 will be equal to, this will be a minus of r divided by mu2 minus 1. And in the question itself, we are given that our f1 is equal to twice of f2. f1 is given as twice of f2. So we substitute f1, that was our r upon mu1 minus 1, and here we have twice r upon mu2 minus 1. R and r can goes away, and we get this as mu2 minus 1 is equal to 2 mu1 minus of 2. So this gives us that 2 mu1 minus mu2 is equal to 1. So this is a relationship between mu1 and v2. And we have this as 2 mu1 minus mu2 is equal to 1. So option number C is the correct one. Option C is correct. So we come to the next question. Here it is given that a convex lens is put 10 centimeter from a light source and it makes a sharp image on the screen, kept 10 centimeter from the lens. Now a glass block, refractive index 1.5 of 1.5 centimeter thickness is placed in contact with the light source. To get the sharp image again, the screen is shifted by a distance d, then this d is. So in this case, we have to find out distance d when the block is being, you can say glass block is inserted and the screen is shifted by a distance d. Okay. So we can divide this question into two parts. One will be without the insertion of the glass block and other will be with the glass block. So first of all, we are given the distance between the light source and the lens. Distance between light source and lens, and that is given as 10 centimeters. We are given the distance between the lens and the screen. Distance between lens and screen, that is also given as 10 centimeter. And we are given the refractive index of the glass block. The refractive index of glass block, that is given as 1.5 centimeter, 1.5, and we are also given the thickness of glass block. Thickness of glass block, that is given as 1.5 centimeters. Okay. So first of all, we are going to calculate the focal length of the lens. Focal length of lens, and for that we can use the standard formula, that is 1 upon f is equal to, this will be 1 upon v and plus 1 upon u. So from here, it is minus, and we substituted the values and we get this as 1 upon 10, and this will be minus of minus 10, and this will be coming as 2 by 10, which will equal to 1 by 5, and this gives us that a focal length f is equal to 5 centimeters. Okay. Now we are going to find out the shift that is being introduced because of the glass block. Shift due to glass block. Let us suppose that is given as S will be equal to T, that is a thickness, 1 minus 1 upon mu. So we substitute the values, we get S, thickness is our 1.5 centimeters, and this will be 1 minus refractive index is 1.5, and this comes as 0.5 centimeters. So shift is 0.5 centimeters. And now we are going to find out, because of the shift, what will be the new object distance. So we find out new object distance, and this new object distance will be the object will be shifted towards the lens. You see, this object is shifted towards the lens. So new object distance, that is our u prime, will be equal to our minus of 10 plus 0.5, giving us minus of 9.5 centimeters. Based on this, we are going to find out new image position, okay, new image distance. So you can say new image distance given as v prime. So we can use the formula that our 1 upon f is equal to 1 upon v prime minus 1 upon u prime, and this comes as 1 upon v prime minus will be plus 9.5, and we get from here that our 1 upon v prime f, we just found it is our 5, and this will be minus 1 second. So this comes as 9.5, and f is equal to 1.95, and this gives us that 5 into 9.5, and this comes as 9.5 minus 5. Let me check 1 second. This is 0.5 and focal length is 20. Okay. So this comes as our plus, yeah, this is minus, and this comes as minus. So ultimately this will be becoming plus, and this will be becoming plus. Now it will be coming as 14 by 5 divided by 47.5. So this gives us that our v prime will be our 47.5 divided by 14.5, approximately equal to 10.55 centimeters. Okay. One second. Let me check whether Okay. Yes. So this was initially correct. That was my mistake. This is a plus, this comes minus, and we have this as sorry. So this is your minus, this will be plus, and now v prime, this is minus. Yeah, this is correct, and this is also minus, and this will be coming as 4.5. Now it's correct one. And now it's correct. Okay, I missed the this border part of the calculation. So next we are going to find out the shift, how much it is will be shifted, and the original was 10, and the shifted one is new one is 10.55. Okay, therefore we can say that the shift in the screen position, the shift in screen position, if given as d, then this d will be equal to 10.55 minus 10, and this comes as 0.55 centimeters. And so this will be 0.5, and this will be away from the lens. So option number C is the correct one. .55 away from lens. So you can see option C is correct. Option C is correct. Next question, and it was asked in the year 2019 mains, and states that a monochromatic light is incident at a certain angle on an equilateral triangle prism suffers a minimum deviation if the refractive index of the material of the prism is square root of 3, then the angle of incidence is. So let us draw an approximate figure for that. So we have equilateral prism, and equilateral prism is there, so this angle of the prism will be of 60 degree. Let us suppose this is our A, B and C, and this is the ray incident, and this is our incident angle, this is normal n, and it will be refracted somewhere here, and this is other normal, let us suppose this is n prime, and this will be a final emergent ray, and we are supposed to mark the deviation, so this will be our deviation, that is delta, and this is our angle R1, and this is our angle R2, and we are supposed to find out that it suffers a minimum deviation. Okay. So for the minimum deviation, we already know that our for minimum deviation, we can say that our R1 is equal to R2, then it will be equal to our A by 2. And let us suppose we call this as R. Therefore, we can say that our R will be equal to 30 degree. Now we can use the Snell's law. Let us suppose we call this as point as P and this point as Q. So Snell's law at P Snell's law at P, and this gives us mu1 sine of I is equal to mu2 sine of R1. Okay, and R1 is nothing but our R. So mu1 is our air, so we can write this as 1 sine of I. Mu2 is given as square root of 3, and here we have sine of our 30. So this gives us square root of 3, sine of 30 is 1 by 2. So therefore our I will be equal to sine inverse of square root of 3 divided by 2, and this gives us that I is equal to 60 degree. So angle of incidence is our 60. So option number C is the correct one. Option C is correct. Next question, and it is asked that the value of numerical aperture of the objective lens of a microscope is 1.25. If the light of wavelength 5000 angstrom is used, the minimum separation between the 2 points to be seen as distinct will be. Okay. So here this is directly based on the formula, and we know the formula for the numerical aperture. We can say our numerical aperture is given as 0.61 lambda and divided by d, and here this d is the minimum separation between the 2 points to be seen as a distinct. This we are supposed to find out. So this d is our minimum distance between 2 points to be seen as distinct. To be seen as distinct. So we can just modify it. From here we can write our d is equal to 0.16 lambda divided by numerical aperture. We substitute the values. We have 0.61. Lambda is given as 5000 angstrom, so 5000 into 10 to the power minus 10. Numerical aperture is given as 1.25. So this gives us a d will be equal to 0.24 micrometer. So option number A will be the correct option. Option A is correct. Next question. It is almost similar but with a resolution limit. And here it is given the diameter of an objective lens of a telescope is 250 centimeter, or the light of wavelength 600 nanometer coming from a distant object. The limit of resolution of the telescope is close to. And the limit of resolution, we already know the formula, that is 1.22 lambda divided by small d. So we have our resolution limit, that is our 1.22 multiplied by lambda and divided by d, where this d is the diameter. So we substitute the values. We get this as 1.22, lambda is our 600 nanometer, and diameter is given as 250 centimeters. So solving this gives us 3 into 10 to the power minus 7 radians. So option number A is the correct one. Option A is correct. Next question, and here also it is based on the resolution, and calculate the limit of resolution of a telescope objective having a diameter of 200 centimeter if it had detect a light of wavelength 500 nanometer coming from a star. So this is straightforward. So we have the limit of resolution of a telescope. And that is given as 1.22 lambda divided by capital D. Okay, and this is represented as theta. So we can write our theta is equal to 1.22 lambda is given as 500 nanometer and diameter is given as 200 centimeter. So this gives us theta will be coming as 305 into 10 to the power minus 9 radians. So option B is the correct one. Option B is correct. We are given next question. And here it states that a system of three polarizers P1, P2, P3 is set up such that the axis of P3 is crossed with respect to that of P1. The pass axis of P2 is inclined at 60 to the pass axis of P3. When a beam of unpolarized light of intensity I0 is incident on P1, the intensity of the light transmitted by the three polarizer is I. Then the ratio of I0 upon I is equal to. So we have three polarizers P1, P2 and P3, and we are given that the pass axis of P3 is crossed with respect to P1 and inclined, the axis of P2 is inclined at an angle of 60 degree with the pass axis of P3. Okay. So first of all, we have three polarizers. So first polarizer is of P1, and we are given that on P1 it is a unpolarized light. So the unpolarized light falls on P1. Therefore, the intensity of light transmitted from P1 intensity of light transmitted from P1 will be equal to I0 by 2. and it is given that the pass axis of P2 is at an angle of 30 degree with P1. We are given that pass axis of P2 is at 30 degree with P1. So therefore the light intensity from P2, you can say the light intensity from P2 will be equal to, from P1 let us suppose we call this as I1. So P2 will be equal to I1, and we have cos square of theta. Here theta is our 30 degree and I1 is I naught by 2, and let us call this as I2. So we can write that of I2 will be equal to I naught by 2 cos square by 30, and this comes as 3 I naught by 8. And next we are given that the pass axis of P3 is at an angle of 60 degree with P2. Pass axis of P3 is at 60 degree with P2. Therefore, the light intensity transmitted from P3, light intensity from P3 let us call that of I3 will be equal to I2 and cos square phi. Here phi is equal to our 60 degree. We substitute our I2, so we get our I3 is equal to, I2 is our 3 I naught by 8 and cos square of 60, and this comes as 3 I naught by 32. And herein this I3 is nothing but, in the question it is given as I. So let us rename this I. So we get that of I is equal to 3 I naught divided by 32. We need to find out the ratio of I naught by I. So we get I naught upon I will be equal to 32 upon 3, and that will be approximately equal to 10.67. So option number C is the correct one. Option C is correct. Next question. It is based on double slit experiment, and it says that in a double slit experiment, when a thin film of thickness T having refractive index mu is introduced in the front of one of the slits, the maxima of the center of the fringe pattern shift by one fringe width. The value of T is, lambda is the wavelength of the light used. Okay. So here we can divide this discussion into two parts. One will be without the introduction of the, you can say, thin film, and other one will be the with the thin film. And without thin film, so let us suppose we have these two source slits. One slit is of S1 and another slit is of S2, and the maxima let us suppose will be somewhere here. This is the position of the maxima, and this is our central bright fringe, where the, you can say, delta x will be equal to 0. And then will be the introduction of the thickness of T, a film, thin film rather, and so this is S1 and S2, and we have introduced, let us suppose, is a thickness of T, and there is a, you can say, the pattern is shifted. Let us suppose it is shifted in upward direction and they meet somewhere here. Okay. Now this is once again our central bright fringe. Okay, so we have to remember that this position is central bright fringe, and here also this is also central bright fringe. And the shift is of 1 fringe width, but here there will be a, you can say, this will be our delta x, but as it is central fringe, the delta x ideally should be equal to 0. Okay, so we will try to exploit that property, and we can use that the central bright at the first position of bright, or we can say the, let us call this as point P. So we can say that our S2P minus S1P should be equal to 0, and that is our delta x should be equal to 0, because this is representation of delta x only. And we can say that our S2P will be equal to our lambda plus L minus, and S1P will be the extension because of the, you can say, this thickness T, and we can write this as L minus T, and this comes as plus mu multiplied by T is equal to 0. And these two are their respective optical lengths. So this is optical length of the first part, that SP2, and this is optical path length of the SP1. So we can further solve it. And we get this as lambda plus L minus L plus T minus mu T is equal to 0, and here L goes with L, and we are left with that our lambda, or we need to find out what T, value of T, so we can just combine T here. So we get T will be equal to, this will be our 1 minus mu is equal to minus of lambda, and this gives us that our T will be equal to lambda upon mu minus 1. So the correct option, I think I, one second, copied the wrong, yeah. So the options which I pasted here are not, because so these are the not of the correct option. Okay. I think I posted the wrong options here. Okay, I'm sorry for that. So the correct option is lambda mu minus 1 will be the thickness. Let me write it here. So T will be equal to lambda mu minus 1. So we come to the next question. And here it is asked that in Young's double slit experiment, the ratio of the slit's width is 4.1. The ratio of intensity of maxima to the minima close to the central fringe on the screen will be. So we have been given the ratio is given the ratio of the slit width is 4:1. Okay, and we know that our intensity is directly proportional to the slit width. You can say our intensity is directly proportional to the slit width, or in the simpler terms we can say that our I is directly proportional to W. And for the from here we can write our I1 and I2, and we can write that our I1 is our 4 times I0, and we can write our I2 is equal to I0 because the ratio is 4:1. And we need to find out the maximum minima. So we know that our I max is equal to square root of I1 plus square root of I2 whole square. We substitute it, we get this as, this will be coming as 4 times I0 plus square root of I0 and whole square, which will be coming as 9 on I0. And next is our I minimum, which will be equal to square root of I1 minus square root of I2. We substitute the same, we get this as 4 times I0 square root and I0 whole square. This will be giving us I0. So the ratio, and that is our I max upon I mean, will be equal to 9 I0 divided by I0. So this comes as 9:1. So the option number C is the correct one. Option C is correct. Next question. The figure shows a Young's double slit experimental setup. It is observed that when a thin transparent sheet of thickness T and refractive index mu is put in front of one of the slits, the central maxima gets shifted by a distance equal to n fringe widths. If the wavelength of the light used is lambda, then T will be equal to. So this is same question which we did previously, and here it is given that the shifted is by n fringe width. So, and we already know that the path difference for the central maxima, that is delta of x, for the with the insertion of the sheet, it is given as mu minus 1 multiplied by t. So you can say path difference at central maxima that is our delta of x will be equal to mu minus 1 multiplied by t, and it is given that the whole pattern is shifted by the n times the fringe width. So we are given that central maxima shifts by n fringe width. Therefore, we can write that our mu minus 1 times t and this is capital D divided by small d will be equal to n lambda capital D divided by small d. Okay. And this gives us that our t will be equal to n lambda divided by mu minus 1. Okay. So this is one of the way of doing the same question, or otherwise we can also do that it is given that central maxima, the difference is always, the path difference is always equal to 0. So in the first case, there will be central maximum something like this, and with the insertion of the thickness t, let us suppose the path difference comes like this, and it is a n times the fringe width. Okay. Same question can be done the other way also. And here you can say none of the option matches, so this correct option is this one. Next question. In an interference experiment, the ratio of the amplitude of the coherent waves is A1 by A2 is 1 by 3. The ratio of maxima and minimum interference of the fringe will be. So here amplitude ratio is given as 1 by 3, and it is straightforward relationship which gives us that our I max to I mean is equal to A2 plus A1 divided by A2 minus A1 and its whole square. And we are given the ratio as A1 by A2 is given as 1 by 3. So we can just modify it. We can say our A2 by A1 plus 1 divided by A2 upon A1 minus 1 and whole square. So we substitute it. We get this as 3 plus 1 and 3 minus 1 whole square, and this comes as 4 is to 1. So option number C is the correct one. Option C is correct. Next question. It is given that in a Young's double slit experiment, the path difference at a certain point on the screen between two interfering waves is 1 by 8 of the wavelength. The ratio of the intensity at this point to at the center of the bright fringe is close to. So here we are given that the path difference of the wavelength is 1 by 8 of the wavelength. Sorry, the path difference between two interfering fringes is 1 by 8th of the wavelength. And so path difference we can write that path difference, that is delta of x, is 1 by 8th of the wavelength, that is lambda by 8. And we need to find out the ratio of the intensity at this point to that of the center of bright fringe. Okay. So first we are going to find out the phase difference. The phase difference, that is our delta of phi, is our 2 pi upon lambda multiplied by the path difference, that is delta of x. Delta of x is lambda by 8, so this we get 2 pi lambda multiplied by lambda by 8. Here lambda and lambda goes, this goes by 4, so we get that our phase difference is equal to pi by 4. Now based on this phase difference, we can easily find out the intensity at a given point. Intensity at a given point, let us suppose that is given as I, and then this I will be equal to the maximum intensity I max, and we have this is cos square and the phase difference delta of phi divided by 2, and delta of phi is pi by 4, so we get this as our I max and cos square of pi by 8. Okay, so this is our intensity at this any point. Okay. And we need to find out the maximum intensity, because at the center fringe there will be only one intensity present, that will maximum intensity. So from here we can just remodulate it, and we get this as I upon I max will be equal to cos square pi by 8. And this can be easily formulated. We can write this as 1 plus cos of pi by 4, and this is divided by 2. Cos of pi by 4 is 1 upon square root of 2 and divided by 2. So this will be approximately equal to 0.85. So option number D is the correct one. Option D is correct. Next question, and it says that consider Young's double slit experiment as shown in the figure. What would be the slit separation D in terms of wavelength lambda such that the first minima occurs directly in front of S1? So first minima should be in the directly in front of S1, that is at P. Okay, and here the distance between the screen and the source, you can say the slits, is given as 2D, and the distance between the two slits is given as D. And we know that the path difference should be our lambda by 2, that is delta of x has to be lambda by 2. So we can say that for first minima, at point P, delta of x should be equal to lambda by 2. Okay. And we can use the triangle property to find out our S1P is directly our 2D, and we can find out our S2P by using the triangle. Okay. So this is our triangle, this is our D, we have this S1, S2, and this is our P. So we are given this distance as D, so we can find out our S2P will be equal to square root of 5 times D. this comes as 5 times d. Now the path difference from, you can say, S2p minus S1p. So we can say delta of x will be equal to S2p minus S1p, and that will be equal to lambda by 2, and by substituting the values we can get this as 5 minus 2d is equal to lambda by d. Let me write it, sorry. So this will be coming as, it much more 5 of d, this way much more clear. Here also we can write this as d square root of 5. So we can take d as common, so this comes as d, and we get this is lambda, and we have 2 square root of 5 minus 2. So the option number C is the correct one. Option C is correct. Next question, and it says that in a Young's double slit experiment with the slit separation 0.1 millimeter, one observes a bright fringe at angle of 1 by 40 radian by using a light of wavelength lambda 1. When the light of wavelength lambda 2 is used, a bright fringe is seen at the same angle in the same setup. Given that lambda 1 and lambda 2 are visible range, that is 380 nanometer to 740 nanometer, their values are. So we are two wavelengths, lambda 1 and lambda 2, and we are given that lambda is within the visible range of 380 nanometer to 740 nanometer, and we are also given the angular, that is 140 radian. So let us write the data which is given to us. So we are given the slit separation, that is d is our 0.1 millimeter. This comes as 1 into 10 to the power minus 4 meters. Angle, that is our theta, is given as 1 upon 40 radians, and the wavelength is given as our 380 nanometer, but less than 740 nanometer. And we are first of all going to find out the path difference. So we have the path difference path difference for small angle approximation. For small angle, we can write that our d sine of theta will be approximately equal to d multiplied by theta, and we are already given the value of d as well as theta. So d is our 1 into 10 to the power minus 4, and theta is our 1 upon 40, and this comes as 2500 nanometer. So path difference, that is our delta of x, is our 25 nanometer. Then we apply for the condition of the bright fringe. Okay. So we can say condition of bright fringe, we can write that our d sine of theta will be equal to n times lambda, and from here we get our lambda will be equal to 2500 nanometer divided by n. And now we are going to find out for what value of n we are going to get the visible range. So we can say possible value of lambda within the visible range. Possible value of lambda for visible range. So let us first take n as 3. We get lambda is equal to 2500 divided by 3, and this comes as 833 nanometer. So obviously it is not in the visible range. Next, let us take n is equal to 4. We get lambda is equal to 2500 divided by 4, and this comes as 6 to 5 nanometer, and this is the within the visible range. Similarly, let us do it for n is equal to 5. We get lambda is equal to 2500 divided by 5. This gives us 500 nanometer, and this is also within the visible range. And finally, let us do it for n is equal to 6. So lambda will be equal to 2500 divided by 6, and this will be coming as close to 416.67. So this is also the visible range. And for n equal to 7, lambda will be equal to 2500 divided by 7. This will be coming as 357, and this will be outside the visible range. And the range which are given to us is 380 to 740. Okay. And or we can say that only 2 wavelengths are required, so we can choose the wavelength. The options that are will be 625 to 500 nanometer. So this will be 2 options, that is option D is the correct one, because we require only 2 wavelengths. So you can say option D is correct. Okay, next question. And it states that in Young's double slit experiment, the slits are placed 0.30 millimeter apart. Light of wavelength lambda 500 nanometer is incident on the slits. The total number of bright fringes that are observed in the angular range of minus 30 degree to plus 30 degree is. So here we are given the distance between the slits, that is our D. So D is given to us, that is our 0.30 millimeter. So we can write this as 0.320 into 10 to the power minus 3 meters. Wavelength is also given as 500 nanometer, and we are given the angular range. angular range, that is our theta, is given from 30 and to plus 30. And we are going to use the bright fringes condition. So we can say for bright fringes, for bright fringes, we know that our d sine of theta should be equal to our n times lambda, and we can write this as our n will be equal to d sine of theta divided by lambda. And we are going to use, you can say, the value of theta, and that is going to help us to find out the solution. Okay. And first value of theta is our 30 degree. Let's do it for positive. So you can say for theta is equal to plus 30. So this gives us our n, and d is our 0.320, and we have this sine of 30, and lambda is our 500 into 10 to the power minus 9. So this gives us that the sine 30 is 1 by 2, and we get this as n will be approximately equal to 320. And the total number of fringes will be equal to twice the maximum value and plus 1, because the central fringe includes at n plus 0. Okay. So you can say that since the angular range, that is our theta, is symmetric about 0 degree, is symmetric about 0 degree, the number of fringes on both sides of center is same, and we can also say the total number of fringes will be equal to twice, because it is symmetric, multiplied by n plus 1, and this plus 1 is because of the central fringe that is at n equal to 0. Okay. So this includes central fringe at n is equal to 0. So we substitute value of n, that is our 320. So we get our capital N is equal to 2 into 320 plus 1. And this comes as 641. So option number D is the correct one. Option D is correct. The next question, and here it states that two coherent sources produces wave of different intensities which interfere. After interference, the ratio of maximum intensity to minimum intensity is 16. The ratio of the waves, the intensity of the waves is in the ratio of. So we are given that the ratio of their maximum intensity to minimum intensity is 16, and we have to find out the intensity of the waves is in the ratio. So we are given that our I max to I mean, it is given as a ratio of 16:1. And we know that our I max is equal to A1 plus A2 whole square, and I mean is equal to A1 minus A2 whole square. Okay. And we know that our I max is equal to A1 plus A2 whole square, and I mean is equal to A1 minus A2 and whole square. And we substitute it, we get this as A1 plus A2 divided by A1 minus A2 whole square is equal to 16. So this gives us that our A1 plus A2 is equal to 4 times A1 minus A2. And we can just sort it out, and we can say that our 5 times A2 is equal to 3 times A1. And from here we can find out the ratio of A1 to A2 is equal to 5:3. But we are supposed to find out the intensity of the wave, that is ratio of I1 upon I2. Okay. And we know that our intensity that is our I is directly proportional to the square of the amplitude. Okay. So from here we can write that our I1 to I2 will be equal to A1 to A2 and its whole square. We simply substitute the values. We get our I1 to I2, A1 is our 5/3 whole square. So this gives us the ratio I1 to I2 will be equal to 25/9. So option number C is the correct one. Option C is correct. Come to the next question. And here it states that a convex lens of focal length 20 cm and a concave mirror having their principal axis along the same lines are kept 80 cm apart from each other. The concave mirror is to the right of convex lens. When an object is kept at a distance of 30 cm to the left of the convex lens, its image remains at the same position even if concave mirror is removed. The maximum distance of the object for which this concave mirror by itself would produce a virtual image would be. So here we are given that the distance of the object is our at a distance of 30 centimeter, and the focal length of convex lens is given as 20 centimeter. So from here we are going to find out what will be our position of the image relative to the convex lens. Then we are going to find out what will be the position of this image with respect to the concave mirror. Okay. So we are going to use the formula that, rather we can say, we are given as u is given as minus of 30 centimeter, and the focal length is our also given as 30 centimeter. 30 or 20? Focal length is given as 20 centimeter. And we can use the formula 1 upon v minus 1 upon u is equal to 1 upon f. So we get our 1 upon v is equal to 1 upon f plus 1 upon u. 1 upon f is 120, and this comes as minus of 30. So from here we get our 1 upon v is equal to, this will be our, let us suppose, 600, and this comes as of 30 minus 20. So this gives a v is equal to 60 centimeters. But this is the position with respect to the convex mirror. Okay. Now we can find out the distance of this image from the concave mirror. Distance of this image from concave mirror and the distance between them is 80, so this will be 80 minus 60 and giving us as a 20 centimeter. And it says that the image remains at the same position even if the concave mirror is removed. Okay. And this is only possible when the object is at a distance of twice of the focal length. You can say that when the object is at twice of focal length and from concave mirror, the image, let us call this as FM for a concave mirror, the image is formed at same position, and therefore we can write that twice of FM, the image position is 20 centimeter for the concave mirror, so twice FM will be equal to 20, so we get that our FM will be equal to 10 centimeters. And we need to find out the maximum distance of the object. Okay, so it means to get the virtual image by the concave mirror, the object distance must be less than the focal length. That is the basic concept behind the virtual image. So we can say for virtual image, by concave mirror, the object distance must be less than the focal length. And here in question we are asked the maximum distance. So maximum distance will be actually equal to the focal length. Therefore we can say that the maximum object distance, will be equal to 10 centimeters. So option number C is the correct one. And C is correct. Go to the next question. And it states that an upright object is placed at a distance of 40 cm in front of a convergent lens of focal length 20 cm. A convergent mirror of focal length 10 cm is placed at a distance of 60 cm on the other side of the lens. The position and the size of the final image will be. Okay, so we have to a combination of convergent lens and a convergent mirror. And we have to find out the final position of the image. Okay, so here we are going to use lens formula as well as the mirror formula in order to find out we need to find out the size also, so we are going to use the magnification also. So the data that is given to us, so object distance from the lens, that is, let us suppose UL will be equal to our minus of 40 centimeter, and the focal length of the lens, let us suppose this is FL, that is our 20 centimeter. Distance between the two, let us suppose that is given as D, is our 60 centimeter, and the focal length of the mirror, that is FM, it is given as 10 centimeter. So we are going to use the lens formula, or you can say for the lens first. So we can say for lens we can write that 1 upon FL is equal to 1 upon VL minus 1 upon UL. So we get 1 upon VL is equal to 1 upon FL plus 1 upon UL. And from here we are going to find out our VL. So 1 upon VL, FL is our 1 upon 20, and this is our minus of 1 upon 40. So this gives us that a VL will be equal to 40 centimeters. And we are going to calculate for its magnification. Therefore we can say the magnification will be equal to our VL upon UL, and this comes as 40 upon 40, and that is equal to minus of 1. Let us call this as ML. Now we are going to this, we can say, now this image, that is VL 40 centimeter, will be acting as an object for the mirror. Okay. You can say the image formed by lens acts as object for mirror, and we need to find out the object distance for the mirror. You can say object distance for mirror. Let us call that a u naught will be equal to, that is our d minus vl. So we get our u naught will be equal to 60 minus 40 will be equal to 20 centimeters. Now we can use the mirror formula. So we can say for mirror, we have 1 upon Fm is equal to 1 upon Vm plus 1 upon Um. And we need to find out our Vm. So we get 1 upon Vm will be equal to 1 upon Fm minus 1 upon Um. We substitute the values. 1 upon Vm is equal to 1 upon Fm, that is 1 upon 10, and this is our minus of 20. This gives us that Vm will be equal to 20 centimeters. Now we can find out its magnification, that is our mm will be equal to, it is minus Vm divided by Um will be equal to minus of 20 oblique 20, this comes as minus of 1. So total magnification that is our m will be equal to m1 into m2. This comes as minus 1 into minus 1 is equal to 1. So you can say the image will be 40 centimeter from the convergent mirror and magnification is 1, so it will be of same size. So you can say 40 centimeter from the convergent mirror. One second. Centimeter. Sure. Let me check whether the data is correct or not, but it doesn't look like. Because it's 20 centimeter from the convergent mirror, not 40 centimeter. For 20 centimeter for convergent mirror, same size. Yeah, everything is with respect to this convergent mirror. So we can see it will be 20 centimeter from the convergent mirror. Centimeter from the mirror, same size. So the option number A is the correct option. Option A is correct. And I think this was the last question. Yeah, so this was the last question. So this is the second part of the, you can say, 2000 mains, and there will be also third part. Some question of 2000 mains are left, so which will be a, you can say, covering during the next video. This completes all the question for this part 2. Thank you.